Hello friends, my name is Mr. Dhawale, Department of Chemistry from RBNB College, Srirampur. In today's topic, we are going to discuss about perhydrophenanthrene. We already discussed regarding perhydrophenanthrene in last lecture. In that case, 3 6-membered rings are fused with each other, but the sequence is, suppose we take here one structure of perhydrophenanthrene. So this is the simple structure, planar structure of perhydrophenanthrene, and that structure contain, suppose these are the 3 rings which are in contact with each other. At that time, suppose we say here A ring is fused with B in this fashion. Suppose we are going to discuss regarding A and C ring. At that time, these both rings are fused with B in such a manner that one carbon atom from both sides is uncommon. Okay, so here if we can change the position of fusion of C ring with B ring, at that time the structure is somewhat different. And what is the different structure? So we start with the perhydrophenanthrene. Okay, in perhydrophenanthrene we are supposed to draw here one structure. Suppose these are the A and B which are same as like in perhydrophenanthrene, but C ring is fused with B in this fashion. Okay, so you remember what are the changes. So the bond which is present here, that can be shifted towards this side, and that's why the joining is 1 2, and here the joining is 1 3. Okay, so you remember this one, A, B and C. If we see here, B ring is in contact with A and C by 1 2 manner. By 1 2 manner, there is no uncommon carbon atom in between ring A and ring C. Okay, then now as like perhydrophenanthrene, we are try to draw the different structures or different possible conformers which are seen in this type of ring fusion. Okay, so the first possible isomer or the possible conformer for perhydrophenanthrene is trans-anti-trans. So first we write here trans-anti-trans. So we write T for trans, which is abbreviated. Anti means also trans, but the fusion is considered as A and C, so that we write here anti-fusion. Then this trans is for B and C fusion. So the hydrogen present on the junction or combined carbon atom, at that time we say here the hydrogen, both hydrogens are not on the same side, so that we write here this is trans. Okay, so suppose we try to draw dot on the carbon atom to show this type of fusion. Okay, at that time we see here, suppose we can write dot on this carbon atom. At that time the fusion is trans for A and B. if we go for A and C fused with B, for this A means anti means this is the trans fusion, okay, this is also present. But when we go for this side, at that time B and C fusion is cis is seen here, but we want trans, so we give a dot on this carbon atom, not on this carbon atom. Why? Because if we draw dot on this carbon atom, at that time both these hydrogens are on the same side, so that there is no anti, it will be a seen, so that we draw dot on this carbon atom, so that B and C fusion is trans, so that again we try to convert that structure into the chair conformation. And in this case here, first we draw our which ring? Students, you remember, first you draw ring B and then you try to draw ring A in concern with the ring C. Okay, suppose this is the fusion of ring A and B, that hydrogen atom is which is present on this carbon atom, which is axial. So first we draw that hydrogens. Here this hydrogen is below the plane, so we write both of these, and then we try to draw remaining bonds which are utilized in the ring formation of A ring. So this is A ring and this is transfused. Okay, so this dot can be represented for the beta hydrogen. Okay, then next the drastic condition is what? How we draw the ring C. Okay, so its fusion is not here, this and this carbon. Okay, why? Because this carbon is uncommon, but in this case there is no uncommon carbon atom in between A and C ring fusion, so that you remember these two carbon atoms are utilized, or these two. Okay, so these 2 points are important for us for drawing the ring C. So what is the position of hydrogen atom present on that? So here this carbon atom having the proton which is axial. Okay, axial, but that proton is at the alpha side, and this proton which is present at the beta axial side. Okay, so remaining 2 bonds on that carbon atom are somewhat look like this. Okay, and here also we draw this one. Okay, then next bonds we draw like this. Okay, so here the shape is somewhat like a ring. Okay, so you remember this one, and here this type of structure you have. And now from this conformation of cyclic ring system and chair conformation, we are going to calculate its theoretical energy. So what is the energy? Here the energy is for this ring, okay, which is above the, or this is somewhat embed on the ring B. Okay, so that it gives somewhat interactions between the axial proton which is present on this carbon atom, so that there is somewhat interaction we show, and we calculate that energy as a 1,3 axial interaction. And in case of 1/3 axial interaction, it gives somewhat 3.34 kilojoule energy, or 13.4 kilojoule energy. So here we can calculate this one, and here one interaction in between this C4 and C5. So we get here 3.35 for one interaction, 1 into 3.35, so we have 3.35 kilojoules is the energy for 1 mole per mole. So carbon 3 and carbon 4 we get here. These two interactions are seen, and this carbon atom also can a part of this interaction, so that it gives one interaction. So that we write here, this is interaction due to the ring present on this B ring, so that it gives this type of energy. Then next type or next conformation, possible conformation for this perhydroanthracene is cis antitrans. We write here cis antitrans, CAT, we call this is CAT, and cis antitrans which we show in this structure also. So what are the points? These are the points. This is the cis. If we give 2 dot on this 2 common carbon atom, at that time this geometry is cis. Why? Because both the hydrogens are on the same side. Then what is the relation in between this A and C? Which is trans, means for anti, and here this relation in between common carbon atom of B and C ring is also trans, so that here we get very easily this type of structure. And according to this, we can try that planar structure which is converted into the simply chair conformation. So this is B, and on this carbon atom we show here, suppose this is one of the hydrogen, and now this hydrogen is a part of this ring, okay, remember, and this is the hydrogen which is also present at the beta side, so beta equatorially it is present. And now the remaining 2 bonds on that carbon atom are this one and this one. So you can try to draw a ring from that 2 bonds, and this is somewhat look of this ring, ring A, which is seen like this. Then next ring C we have, and that ring contain this hydrogen atom is at the alpha side and this is at the beta side. So the ring which is seen in earlier structure is somewhat same like this, so that we draw very easily on that ring. So here in case of these 2 ring we have this one interaction is seen, but for this ring which is cis to this one, it gives 3 interactions for gauge butane segment. So here in this cis decalene, when we go for cis decalene, at that time it gives 3 interactions, and that interactions are nothing but the butane gauge interaction, and that 3 interactions are also add in this one interaction which is due to the C ring. Okay, so here commonly we have 4 interactions. So we write here 4 into 3.35, we get here the final value which is 13.4 kilojoules. 13.4 kilojoules per mole. Okay, so you remember this one. Then we go for next conformation, and that conformation type is cis sin cis. Cis sin cis. Okay, this cis sin cis contain, if you write all the dot on this common carbon atoms, or you don't write dots, or you don't keep or give a dot on this carbon atom, so all these things are the same. Okay, so here we write all these dots, and here we say this is cis, this one is sin, and this one is cis. Okay, so you remember this one. So this structure is for cis, sin, cis. And now we try to convert that structure into the chair conformation as like. So here we write the structure of B ring. First we draw chair of B ring. So this is the B ring. The next one you choose the carbon atoms. So here as like this one, this is one of the beta axial, this is beta equatorial, and these 2 bonds are remaining bonds. So you draw this type of chair as like this one. So here 3 interactions are your pre-calculated, Then next we draw for this cis, which is present on this. So all these hydrogens are on the beta side, so that we draw this is the equatorial beta and this one is the axial beta. So these two bonds are remaining. Which two bonds we have? So this is first bond and this one second bond. So these two bonds are also remaining, but we try to draw that on this carbon atom, so that this is one of the proton and this one is also one of the proton, which is at the beta side. So you can write that chair instead of here, we can try to draw here. Okay, and so what is the actual position of this bond, remaining bond, which is present on this carbon atom at here? Okay, which are I write here, I draw that bond by dot. Why? Because this is our actual representation, but when we draw that bond on the actual position, at that time there is no ring formation, or there is no such a structure which can give the chair form or a chair like structure. So here for our convenience we can change the position of that bond, and we try to draw a chair conformation from that bonds, remaining bonds. So this type of structure you have seen like this. Okay, but what is the actual position of this bond? This is like this one, okay, which is on the side of this deep carbon atom and it is somewhat tilted. But here for our convenience we can change the position of that carbon bond, and we have this type of nice chair. Okay, so in this case here this structure is, I think, highly energetic structure in this conformations, all these conformations which are seen in the possibility. But when we see on the towards the structure, at that time you see here both the rings are on the same side, so that huge amount of interactions are there. So if you say here, suppose we can hide this C ring, at that time you see this rings, two rings are somewhat look like cis-decalene. So here the pre-calculated energy for that is 13 butane-Gauch interactions are seen and 3 butane-Gauch interactions, so that here we have these 3 butane-Gauch interactions are seen. And but when we hide A ring, at that time also here the relation between B and C is also C, so that there are also 3 butane-Gauch interactions. So total 6 butane-Gauch interaction due to A and C ring, both are cis to the ring B, so that the huge amount of energy is seen. 6 into 3.35. So what is the total energy? And that total energy is nothing but the 30.1 kilojoule. 30.1 kilojoule per mole. Okay, and here the calculated energy for this is not actually equal to the 30.1. Why? Because this is somewhat less, and this B has been calculated when both the rings are on the same side. At that time it can increase the actual energy, so that the total energy is near about 30.1. When we calculate 3.35 into 6, this is not equal to this one, but the total energy is 30.1. Why? Because both the rings are also on the same side, so that there are also interactions as like one-3-diaxial interaction. You see such type of interaction in this case also, so that 3 butane-Gauch and 3 butane-Gauch, 6 butane-Gauch interactions we are pre-calculated. But this both rings are on the same side, at that time the huge amount of bulk is on the same side, so interactions are more, and it gives such a type of huge energy, so that this is one of the high energy structure for perhydrophenanthrene. Okay, and next one is cis anti-cis. Okay, and remaining 3 structures we seen on next lecture. Thank you.